right, so here we go. Steps to hearing. There's no particular quantity of steps. I mean, if you really break it down into, each individual thing, you can probably put like 40 or 50 things here. I'm going to try to simplify it just a bit. Yeah, just about one page or so. Yeah. Okay, here we go. First, sound waves are produced. And that could be from any place. Right now I'm hearing the freezer in the classroom, music really kind of faint, my own voice, students snoring. Not yet. Never looked around though. I appreciate that. All right. So those sound waves that are produced are basically disturbing the air around us, and we are then going to collect that. So sound waves are gathered by the flap on the outside. What's that thing called? The pinna, sometimes called the auricle. But that's the whole assembly on the outside. And sent through the tube. What's the tube called? External auditory canal. I said that earlier and somebody said the EAC, dude. I was like, little Nemo reference there. External auditory canal to the, what's the real name for the eardrum? Tympanic membrane. There's a reason, though. There's a reason we have a tympanic membrane to begin with, because if what happens next didn't need to happen, you hear like birds chirping. Yeah. That's really ironic. Like we're talking about hearing, and then we're hearing like faint birds chirping.
Where are they coming from?
I'm not sure. They fly in here, we'll know. Okay. Tympanic membrane absorbs sound waves. Oh, sorry, right on the line. And vibrates all kinds of sounds today. Vibrates the auditory ossicles. Folks, what are the auditory ossicles?
Your ear bones.
Ear bones. AKA the malleus, the incus, and the stapes.
The hammer, anvil, and stirrup.
Yep. But there has to be a reason. Always got to be a reason. Here's why. The auditory ossicles amplify the waves. The way the ear bones are set up, they take small waves and turn them into huge waves, waving back and forth a ton. And that's really important. See, otherwise, if sound waves were enough, we could just have the eardrum gone and all the bones gone, and sound could just hit the oval window of the cochlea and create enough sound or create enough energy to do that. But it's not enough by itself. So we need our eardrum to gather these really small waves, these subtle waves, vibrate back and forth, and cause the ear bones to amplify that. The last ear bone was called what, gang? The last one in the line is called the stapes. Stapes. Okay? The stapes attached to the oval window causes pressure waves in the fluid of the cochlea. Snail looking thing. So the stapes, which is attached to the oval window, causes pressure waves in the fluid of the cochlea. The fluid, I'm going to put in parentheses, two different kinds. One called paralymph and one called endolymph. Alright, there's a whole lot of conceptual things, a whole lot of descriptions of using words, no pictures. Let me give you some pictures here. Don't worry, we're not drawing them. Okay. Show from the beginning here what we're doing. First step that we've got written down, sound waves are produced. So, something out here creating sounds. It's going to travel down. It's gathered by the pinna. Going to travel down the external acoustic canal or external auditory canal. Causes the eardrum to vibrate ever so slightly. Little movements of the eardrum, because of how the bones are positioned here, are going to turn into big movements of the stapes. Going to vibrate back and forth in a way that corresponds with the type of sounds that we hear. Now, what's neat about this is that the cochlea, this snail-looking thing, is completely encased in bone. The only place for pressure to go in is right here. The only place for pressure to be relieved is right here. Pressure goes in at the oval window and is relieved at the what? Round window. So, as the stapes pushes in here on the oval window, what happens to the round window? It bulges out. And as the stapes pulls back, the round window will go in, okay, because this is filled completely with fluid. Two different kinds of fluid, but filled with fluid nonetheless, okay? Now, what happens then is this. We have in the cochlea, those pressure waves are going to travel through, okay? So this is like pressure going in, and it will go through into the cochlea like that. It'll travel around, and it will cross over this little blue membrane, which is the cochlear duct, and that has all the stuff that senses sound. It'll cross over at a place that is equivalent to its frequency. Let me try to break this down for you. You know, cochlea looks like a snail. It goes out and it wraps in on itself a bunch of times like that. But if you laid it flat, like if you unraveled the whole thing, you'd find out the reason why we need so much of it. You see, each of these little sections of the cochlea responds to different frequencies. The higher pitches that we hear, really, really high pitches, are toward the beginning, because those waves cross over here. Where they're shorter, they cross over here. But because these waves that are going to be over here are longer, they're further apart, we're going to process those deeper into the cochlea. So the sounds that we hear that are really, really deep in sound are ones that are going pretty much all the way into the cochlea. They're traveling all the way into the center here to be processed. Whereas high-pitched sounds are getting processed right about here, toward the beginning of the cochlea. Now, how is it processed? Okay? That fluid, the waves in the fluid are going to cross over. Now this is a cross section of the cochlea, all right? And it's going, that fluid pressure wave is going to cross from here to here, and as it does, it disrupts something called the organ of Corti. Let's write a couple more things, and then we're going to come back to this idea here again, and I'll explain the process, okay? So, waves in the perilymph are transmitted through the cochlear duct. Through the cochlear duct. Okay, let me show you a picture of this then. Come back to here in just a second. All right, so watch this. This right here is called the vestibular duct, and it's filled with perilymph. Down here is the tympanic duct, and it's filled with perilymph. This right here in the middle is the cochlear duct, and the cochlear duct is filled with endolymph. This is where hearing occurs, is right in this area. Where these waves cross over like this through the cochlear duct will correspond to the frequency. Lower frequencies are going to travel through quite a ways before they cross over. Higher frequencies are going to cross over rather quickly, but it's right here, gang. It's right here that hearing occurs. And something called the organ of Corti. Now, if we take this and do a cross section of it, this is what it looks like. So pressure waves are traveling from here and crossing here. This little boxed in section right here is called the organ of Corti. And it looks like that. We're going to make a very simple example with our hand. So take your hand like this, and take your other hand and put it on top like that. All right. This hand down here represents the specialized cell with these cilia on it. And because of these cilia, this cell is called a hair cell. This membrane on the top is called the tectorial membrane. Now, as I'm talking, the pressure waves are traveling through, pressing the tectorial membrane into the cilia of the hair cell. Does that make sense? So every time there's any type of sound that you're hearing, it's happening because pressure waves are passing across and stimulating the cilia of this hair cell. Now there's lots and lots of hair cells. Quiet sounds stimulate like this. Not very much. Loud sounds stimulate a lot of stuff. A few hair cells more than quieter sounds. Rock concerts, things like that, listening to your headphones, just smashing stuff. Okay, not good for the hair cells, all right? Viewers at home, this hair cell's sad. Look at him. Shine the light on him. You know when you hear really... Go into the light, little hair cell. Yeah, viewers at home, I'm out of my mind. Okay, so here's the thing.
We know, Lily. We know.
You know that sound you hear in your ears when you've listened to something too loud? That's the flat line for this guy. He's dead now. Yeah, sorry. That was weird. So they say it's a swan song. Have you ever heard that term before? Swan song is like swans only sing once in their life, and it's right before they die. That's really sad, isn't it?
Oh.
Happy notes for people at home. But they say it's the swan song of the hair cells. Now, here's the thing about your hair cells. Ready? The ones you're hearing me with now are the same ones that you heard your mother with while you were in the womb still. And they're the same ones you'll have when you're 80. They don't reproduce, which is why as we age, we lose our hearing, because these cells don't last forever. But they try to last the duration of your lifetime because they can't do mitotic division. Anyway, so that's basically what's happening. So pressure waves coming through here, through this cochlear duct, which is this little area, cause the tectorial membrane to rub up against the hair cells. When things sound loud to us, they sound loud because there is a lot more hair cells stimulated. The quieter sound, the fewer hair cells are stimulated because we have inner ones which respond to lesser sounds and then outer ones that respond to greater sounds. Okay.
Mr. Helly,
Yes.
would you tell Brianna Duncan that she'll be picked up after school where she was left off this morning?
Okay.
Thank you.
All right. Do I need to say that again? Okay, I didn't think so. All right.
So are they always constantly going like those hair cells?
They are. If you're hearing any sound at all,
So
then
like,
they're.
even if like you're like what about that one room where like they blocked out all the sound?
Yeah.
You know, that is a great question.
But like you're hearing your own heartbeat and your own like blood, so that would be going. But is that internal sound or because you're not? It's not an outside.
But is that necessary?
But is any sound an internal sound? If we hear it at all, it's because our ears are processing it. The thing about hair cells is this. They're always sending information, but basically that tectorial membrane will change the firing rate of them. So they're always firing in some way, you know. So, but that's a really good question. Maybe the reason an anechoic chamber drives us crazy is because we need that stimulation and yeah. All right. Question.
Okay, so like if you hit your head or something, oh yeah, I know. What happens to your hair cells? Like, you know,
Yeah,
trauma or something.
that's a terrific question.
Your brain's like
And there's two parts involved. I mean, you have to hit your head pretty hard for that, but there's the part. What we're talking about here is just is the machinery that picks up sound. Then there's also the part where your brain interprets what you hear, and if the brain is injured or damaged, it could hinder the ability to process the sound that goes through. That's just my best guess. I really don't know for sure, but a very good question. Okay, inside the cochlear duct is the organ of Corti.
Are we done with the steps?
We've got something else. This is not really a step. This is just kind of information. Okay. And then we can go to step 7. Waves sent through the cochlear duct. And I think of all the things, this is probably the most important.
How many steps are there?
We're going to end up with 9. No problem. Waves sent through the cochlear duct cause the tectorial membrane to brush against the cilia of the hair cells.
What's that word after cochlea?
Where are we at? Sent through the. Oh, why did I write cochlear? All right, yeah, it should just be cochlea. Cochlea cause the tectorial membrane to brush against the cilia of the hair cells. Sorry about that, gang. All right. This is another important piece here. Just like with balance and equilibrium, movement of the cilia causes the firing rate of the hair cells to change. Why that matters is our last step. Information about frequency and intensity. Is relayed to which lobe? Temporal lobe. Is relayed to the temporal lobe of the brain. It does make one stop along the way. It stops at the mesencephalon before it gets there, because it's attached. It's vestibulocochlear nerve. It's attached to both the vestibule and the cochlea. Passes via which cranial nerve is that? Number 8. Yeah. Cranial nerve number VIII, known as the vestibulocochlear nerve. Sometimes called the auditory nerve because it's easier to spell. But that's pretty much it.